Hi, welcome to Aviation Theory. In this video, we will look at the concepts of QNH, QFE, and QFF, which are used for both altimetry and surface pressure analysis. So, let's get started. In the previous video, we said that in order to perform a surface pressure analysis, atmospheric pressure data is collected and compared between different weather stations. However, a key aspect was that all stations had to be at the same level. This is because to correctly analyze pressure variations horizontally, all pressure measurements must be made at the same level or altitude. Let's see an example to understand this better. Suppose that we have 4 weather stations reporting their atmospheric pressure. In this case, stations A and B are at the same level, specifically at 1,000 feet above mean sea level. And on the other hand, stations C and D are at an elevation of 3,000 feet. With this in mind, let's say that with the intention of performing a surface pressure analysis, all 4 stations report their pressure at 10 a.m. In this situation, there is no problem if we directly compare the pressure of A and B, since both stations are at the same level. And in the same way, there would be no problem in comparing the pressure of stations C and D either. Now, the problem arises if we try to compare, for example, the pressure of stations B and C, because there is not only a horizontal variation, but also a vertical variation, since they are not at the same level. For this reason, it is just not possible to directly compare pressure between stations with different elevation. So, having understood this, here is where the first concept comes in, the QFE. This is simply the atmospheric pressure measured at the station. In other words, it is the pressure measurement obtained directly from the barometer at the station. So, according to what we said previously, we could compare directly the QFE between stations that are at the same level to determine high and low pressure areas. But what we cannot do is compare the QFE between stations at different elevations. Now, the question is, how can we solve this problem? Well, let's look at the following example. Here we have 2 weather stations, one at sea level and the other at 3,000 feet. Let's now say that both of them report their current pressure, or QFE. In this case, if we were to directly compare the 2 pressures, we could think that station A has a lower pressure than station B. However, according to what we said previously, we just cannot make this comparison. So, a possible solution for this could be to determine the pressure of station A if it were at sea level. But how can we do this? Well, the most accurate way would be to dig a deep hole and lower a barometer down to sea level and see what pressure is indicated. This way, since both pressure measurements are made at the same level, we can now compare the two and determine the actual horizontal pressure variation. Now, obviously in practice we don't do this literally. Instead, the approximate value of the pressure at sea level is calculated for each station. This procedure is known as reducing the pressure to sea level and is performed all over the world, since as an international agreement, to compare pressure at different stations at different elevations, all measurements must be reduced to mean sea level. Now, something to keep in mind is that in order to do this procedure, it is necessary to know the rate at which the pressure changes with altitude, or in other words, the vertical pressure gradient. And as we said in previous videos, this gradient varies with altitude and temperature. However, for this example, let's assume it is 1 hectopascal for every 30 feet. With this in mind, let's say that station A is at an elevation of 3,000 feet and is reporting a QFE of 908 hectopascals. If in this case we want to reduce that pressure to sea level, then taking into account the vertical pressure gradient, we could make a simple rule of 3. If the pressure changes by 1 hectopascal for every 30 feet, then how much would it change in 3,000 feet? Well, after doing the math, we obtain as a result that it would change 100 hectopascals. What this means is that the pressure difference between 3,000 feet and sea level is around 100 hectopascals. And since we know that pressure increases as we go down, then we can say that the pressure of the station reduced to sea level is around 1,008 hectopascals. So, Having understood this, let's move on to the next concept, the QNH. This is the atmospheric pressure measured at the station, reduced to mean sea level assuming standard temperature conditions. Let's see what this implies. Let's suppose we have the same situation as before, and the station reports a QFE of 904. Now, under standard conditions, the temperature at 3,000 feet is 9 degrees Celsius, so we will assume that temperature to calculate the vertical pressure gradient, regardless of the actual temperature conditions at the station. So, let's say that under these conditions, we calculate a pressure difference of 105 hectopascals, resulting in a pressure at sea level of 1009. Or in other words, the QNH is 1009. Now, calculating the QNH is not so simple, since the correct vertical pressure gradient to be applied must be determined as a function of the standard temperature as we descend. But we will not go into detail on this. The QNH is very useful for altimetry, since barometric altimeters are calibrated and designed to use standard conditions as reference. However, if what we want is to analyze horizontal pressure variations for weather observations and forecasts, it is necessary to take into account the effect of the actual temperature, which means that the QNH is not useful anymore. The thing is that, as we said in the previous video, the rate at which the pressure changes with altitude varies with air temperature. For instance, at sea level under standard conditions, the pressure changes by 1 hectopascal for every 27 feet. However, if the temperature increases, then the pressure will reduce more slowly with altitude, resulting in a lower vertical pressure gradient. While if the temperature decreases, the pressure will reduce more rapidly with altitude, and we will have a higher vertical pressure gradient. So, with all this in mind, we can move on to the next concept, the QFF. This is the atmospheric pressure measured at the station, reduced to mean sea level, but now using actual temperature conditions. This means that, unlike the QNH, the current temperature is taken as a reference to determine the actual vertical pressure gradient, thus obtaining a more accurate and realistic sea level pressure value. This way, if we were in the same situation as in the previous example, and if we had a high temperature at the station, the pressure would change more slowly with altitude, which means that the pressure difference between 3,000 feet and sea level would be smaller. In this case, only 93 hectopascals, giving as a result a QFF of 997. Now, if under the same conditions the temperature drops and it is now much colder, this means that the pressure will change more rapidly with altitude, resulting in a greater pressure difference between 3,000 feet and sea level. In this particular example, the difference is 104 hectopascals, resulting in a higher QFF of 1008. So, as we could see, in both cases, the QFE did not change. The only thing that changed was the temperature, and that was enough for the QFF to change. Now, it is evident that in order to calculate the QFF, we need to know the vertical pressure gradient for a specific temperature. But how can we determine it in the first place? Well, we can apply this formula to calculate the gradient to be assumed. Now, something important to bear in mind is that the pressure is assumed to change at this constant rate down to sea level. So it is not necessary to correct for temperature changes as with QNH. In other words, the pressure gradient calculated at the station will be applied throughout the entire reduction to sea level, thus obtaining a linear graph like this. Let's see a couple of examples of how we can apply this formula to determine the QFF. Let's say we are at an elevation of 3,000 feet with a QFE of 908 hectopascals and a temperature of 30 degrees Celsius. With this, the first step is to calculate the vertical pressure gradient using this formula. So, in order to do it, we have to change from 30 degrees Celsius to Kelvin, which is done by adding 273 degrees, thus obtaining 303 Kelvin. Having done this, we just have to replace the temperature and the pressure in the formula and do the math. And the result is that under these conditions, the pressure changes by 1 hectopascal for every 32 feet. So, with all this information, we can now calculate the QFF by applying a simple rule of 3. If the pressure changes by 1 hectopascal for every 32 feet, then how much will it change in 3,000 feet? We just do the math, and we get a pressure difference of 94 hectopascals, which means that the QFF is 1002. Now, there is another way to get to this result, and it is by applying this other formula, where we just have to replace the values and directly obtain the QFF. However, it is up to you if you want to use this formula or the rule of 3. Now, so far, we have seen the case of a higher than standard temperature. Let's now look at what happens with a low temperature. In this case, we have the exact same conditions as before, but now the temperature at the station is 2 degrees Celsius. So, we follow the same steps. First, we calculate the vertical pressure gradient using the formula, and as we can see, now the pressure changes by 1 hectopascal for every 29 feet. So, with this in mind, we apply the rule of 3, and we obtain a pressure difference of 103 hectopascals, which results in a QFF of 1011. And just like we said before, we can apply the other formula, and we will get to the same result of 1011. So, now that we know what is QFF and how it is calculated, then we can say that if all weather stations calculate and publish their QFF, horizontal pressure variations can be correctly analyzed, even if the stations are at different elevations. This allows to determine high and low pressure areas objectively, as well as to draw the corresponding isobars in surface analysis charts. Now, with all that we have seen so far, we can summarize that the QNH is mainly used for altimetry purposes in air operations, while the QFF is used by meteorological services to study the surface pressure behavior. However, this implies that there is a certain relationship between these two concepts depending on the temperature. Let's look at the following example to understand it better. In this case, we have 2 stations under the same exact conditions. The only difference is that station A has a temperature of 28 degrees Celsius and B is at minus 15 degrees. So, to calculate the QNH, remember that we are not considering the real temperature. We simply assume standard conditions and reduce the pressure to sea level accordingly, obtaining 1010 in both cases. On the other hand, to calculate the QFF, we actually have to consider the current temperature at the station, and since these temperatures are so different, then the resulting QFF will be different in both cases. In the case of station A, since the temperature is above standard, then the QFF will be lower than the QNH. In this particular case, 1005. And on the other hand, in the case of station B, since the temperature is below standard, then the QFF will be higher than the QNH, specifically 1016. In summary then, QFE is the atmospheric pressure measured at the station, directly from the barometer. It is used sometimes in altimetry to determine the height of an aircraft in relation to the airport elevation. However, that is not so common. Then, QNH is the station pressure reduced to mean sea level, assuming standard temperature conditions. It is widely used for altimetry since it allows to determine the altitude of an aircraft in relation to mean sea level. And finally, QFF is the station pressure reduced to mean sea level, assuming real temperature conditions. It is mainly used by weather services for observations and forecasts, and it can be determined by means of these 2 formulas. Now, before finishing, we must say that in altimetry, there is an additional term known as QNE. This term is used to refer to the pressure at sea level under standard conditions, and it is equal to 1013 hectopascals or 29.92 inches of mercury. If you want more information about altimetry and how all these concepts are used in practice, you can watch the videos about it in the flight instruments section. I hope the information presented in this video was useful. If so, don't forget to share, like, subscribe, and leave a comment down below. It would help me a lot. Thanks for watching, and I see you next time.